All right, today we're diving into a really fascinating new paper that proposes a fundamental shift in how we think about large language model architecture. The goal here is ambitious, to forge a real, tangible connection between high-performance AI and the actual computational principles of the human brain.
And this really gets to the core question the Dragon Hatchling paper is trying to tackle. This isn't just about tweaking a model for slightly better performance. It's about challenging a core assumption in the field, the idea that top-tier performance and biological plausibility have to be two separate, mutually exclusive paths.
So to set the stage, the research starts by looking at the major hurdles in the field right now. The authors frame this as a significant barrier on the path to what they call universal reasoning models.
As the paper lays it out, this barrier is really made of three distinct, tough challenges. First, you've got the problem of getting models to generalize their learning over time. Second, there's this ever-widening gap between our best-performing architectures and the ones that actually look anything like a biological brain. And third, of course, is the classic black box problem, the fundamental lack of built-in interpretability in our most powerful systems.
So in response to all of this, the authors introduced their novel architecture, and they've given it a pretty cool name, the Biological Dragon Hatchling, or BDH for short.
Now, the definition here is really important. BDH isn't just another iteration of what we've seen before. It's being presented as a completely different paradigm. It's built on a network of what the authors call neuron particles, these computational units that interact locally, all arranged in a scale-free graph structure. And that structure is a direct nod to the architecture of biological neural networks.
Of course, for any new architecture to be taken seriously, it has to prove itself against the current champions. So a huge part of the paper is dedicated to rigorously benchmarking the BDH against the transformer architecture, looking at both performance and scaling laws.
This table gives us a fantastic side-by-side comparison. You can see the core architecture is completely different. We're moving from global attention to these local particle interactions, but, and this is crucial, the scaling laws look remarkably similar to transformers. The authors report that BDH actually rivals the performance of models like GPT-2 on major language and translation tasks, and this is at comparable parameter counts, anywhere from 10 million all the way up to 1 billion. And maybe most importantly for practical use, it has a GPU-friendly formulation.
Okay, this brings us to what is arguably the most significant claim of the whole paper, the model's biological plausibility. The authors aren't just saying it's inspired by the brain, they're arguing that it actually functions like a brain model in some very key ways.
I mean, just let that statement sink in for a second. This is a profound claim. It suggests the model's working memory isn't some abstract mathematical trick. Instead, it's grounded entirely in synaptic plasticity, specifically Hebbian learning. The whole neurons that fire together, wire together principle, and it's implemented with spiking neurons.
The paper then lays out this very direct observable mechanism. So when BDH processes or reasons about some concept, specific neurons fire. This firing then directly causes the strengthening of individual synaptic connections. This isn't just an analogy for learning, it's the proposed computational process for how the model remembers and learns during inference.
And the parallels to biology don't stop at the learning rule. The whole network structure is designed to mimic the brain. It's built on a graph with high modularity and a heavy-tailed degree distribution. We have a few highly connected hub neurons, and most others have very few connections. Both of these are hallmark properties of real biological neural networks. The authors even go so far as to propose that this kind of architecture could be a possible mechanism for how our own neural circuits achieve speed.
So, we've covered performance and biology. The third pillar of this work is tackling that persistent challenge we talked about earlier, interpretability. And the approach here is to make transparency a core feature of the design, not something you try to bolt on afterwards. The claim they're making is for inherent state interpretability. What that suggests is an ability to understand the model's internal state in a much more holistic way, to move beyond just probing one neuron at a time or trying to decipher massive parameter matrices. So how does this actually work under the hood? Well, the technical justification comes down to two key properties. First, the model's activation vectors are sparse and they're positive, which makes the job of decoding what the model is representing at any given moment much, much simpler. And second, the paper shows evidence for monosemanticity, meaning that individual neurons tend to latch on to single distinct concepts, which makes figuring out their function way more straightforward. So, if we pull this all together, the biological dragon hatchling is presented as a synthesis of three pillars that we've often been forced to treat as trade-offs: achieving transformer-like performance, maintaining deep biological plausibility, and building in inherent architectural interpretability. And this leaves us with the paper's final provocative question.
By tying top-tier performance to real biological principles like synaptic plasticity and brain-like network structures, has this work actually found a kind of missing link? It's a question that really challenges the current trajectory of AI research and forces us to rethink its relationship with neuroscience.